We live in the information age. But honestly, it's starting to feel more like the misinformation age. Everywhere you scroll, someone's got a new cure. We see people claiming ginger curing deadly cancers, or neem leaves reversing diabetes. And apparently, maldapaverin can prevent heart attacks. The internet has turned everyone into a part-time doctor and full-time myth spreader. Unfortunately, even doctors don't fully understand the scientific process. So how do we tell what's true and what's just internet nonsense? It's actually simple. We have something called the scientific process. Let's dive deeper and see how science helps us make sense of this mess. Real research begins with a question. Does exposure X relate to outcome Y? For example, you might be interested in knowing if smoking, your exposure of interest, is associated with lung cancer, your outcome of interest. And if obesity can lead to high blood pressure, or a particular drug can treat certain cancer. So, how does real research actually work? We follow a simple, powerful framework, the so-called 3+1 Cs. Step 1 is all about finding a connection. That's where comparison, confidence, interval, and confounders come in. Don't worry, we'll unpack each of these in just a moment. Step 2 is about proving it's real, moving from correlation to causation. Let's try to understand both the steps with the help of an example. First, the comparison. Say you're testing if a drug X or a food X can lower blood pressure. You run your experiment and collect the data. Turns out, the group taking drug X has a systolic BP that's 10 points lower. Not bad, but before celebrating, let's see if this difference is real or just random luck. Now comes the second C, the confidence interval. The 10-unit difference we found is just in a sample of our 200 participants. But what about the entire city? Thousands of people who did or didn't take the drug. We can't measure everyone's blood pressure, so we use statistics to estimate what's true for the whole population. We'll never know with 100% certainty what the true difference is in the entire population. But statistics can help. They let us estimate with 95% confidence the range where that true difference likely lies. This is called a 95% confidence interval. Don't worry, you don't have to calculate it by hand. The computer can do it for you. Here, our interval runs from -5 to -15, meaning we're 95% sure the true population difference lies somewhere in that range. Since the whole range is below 0, we can say the difference is statistically significant. In short, drug X really seems to lower blood pressure. But if the confidence interval runs from +5 to -20, notice it now includes 0. That means the difference might not be real. So, in this case, we can't be confident the drug X truly lowers blood pressure. It's not statistically significant. Now for the third C, confounders. Even if we see a clear difference in blood pressure between those who took the drug and those who didn't, other factors might be at play. Maybe the drug users were younger, had lower cholesterol, or exercised more. These hidden influences are called confounders. There are two main ways to control confounders. The first is randomization. You randomly assign people to groups. For example, if you're testing a drug, you randomly pick who gets the pill and who doesn't. That way, everything else like age or lifestyle is evenly mixed between groups. The second method is statistical, using regression. Here we adjust for confounders like age, diet, and cholesterol to compare similar people. If after controlling for all these factors, the difference still remains, we can say with more confidence that drug or food X truly affects blood pressure, not just the other variables. Now comes the final C, causality. In research, we often say correlation is not causation. Or better yet, correlation alone is not causation. It's just one piece of the puzzle, not the whole picture. Once we've found a correlation, the next question is it actually causal? To figure that out, we need to confirm a few key things. There should be a reasonable biological mechanism connecting the exposure and outcome. 2. The findings should repeat in different studies, places, and populations. An exposure must precede the outcome. Not the other way around. The outcome should vary proportionally with the level of exposure. I hope I managed to condense years of scientific reasoning into just 5 minutes. Thanks for watching.